We start today with an example called the binomial series. It's for finding Taylor series expansions for functions of the form 1 plus x to the p power for any value of p whatsoever. It doesn't matter what p is. Usually when you think about something called the binomial theorem, p is a positive integer like 1 or 2 or 3 or 4 or 5, etc. And you could expand this with Pascal's triangle. But as an infinite series, we're more interested in unusual values of p, you might say, like fractions or maybe negative numbers. In fact, for example, if p is -1, as an example, then f of x is 1 plus x to the -1 power. That's 1 over 1 plus x, and that is a function we derived the Taylor series for last time. In fact, that's most easily derived by seeing it's a geometric series, the sum of a geometric series with first term a equals 1 and common ratio r equals -x. Therefore, it sums to a plus ar squared plus ar cubed, which turns out to equal this. As long as that common ratio is less than 1 in absolute value, in this case, absolute value of -x is less than 1, which means absolute value of x itself is less than 1, which means x is between -1 and 1. So we already know what the answer is when p is -1. You also, in your homework, I believe, did consider examples like p equals 1/2. If p equals 1/2, then it's 1 plus x to the 1/2 power, which is square root of 1 plus x. You did examples like that. I'm not going to say what the answer is at the moment. If p is a third, then you've got the cube root of 1 plus x. I believe you had an example like that. But let's find the Taylor series centered at a equals 0. So we use a equals 0 as we do at least 90% of the time. Centered at a equals 0, no matter what p is. By finding derivatives, f prime is going to be p times 1 plus x to the p minus 1 power. Technically, the chain rule would say multiply times the derivative of 1 plus x, but that's 1. I can certainly write times 1 for emphasis, but of course, when you multiply by 1, nothing changes, so I don't have to write times 1. F double prime of x, differentiate again, you get p times p minus 1 times 1 plus x to the p minus 2 times 1. Differentiate again, f triple prime of x will be p times p minus 1. I bring down a p minus 2, subtract 1 from the exponent and make it p minus 3, etc. The next one would be p times p minus 1 times p minus 2 times p minus 3 times 1 plus x to the p minus 4. But now we want to plug in 0 into all these things because we're expanding about a equals 0. F of 0 is 1 to the p is 1. F prime of 0 is p times 1 to the p minus 1 is p. F double prime of 0 is p times p minus 1 times 1 to the p minus 2. Again, 1 to any power is 1. So we get that. F triple prime of 0 is going to be, in the end, p times p minus 1 times p minus 2. The pattern continues. F quadruple prime of 0 would be p times p minus 1 times p minus 2 times p minus 3. So the Taylor series, call it p sub infinity of x. Sub infinity because it's got infinitely many terms. It's an infinite series. It's not a Taylor polynomial. It's a Taylor series. Is f of 0 1 plus f prime of 0 p times x minus 0, right? the Taylor series formula, you always have powers of x minus a, where a doesn't have to be 0 except 90% of the time or more, it is 0. X minus 0 is just x. Plus f double prime of 0, this thing, not by itself, but over 2 factorial. P times p minus 1 over 2 factorial times x minus 0 quantity squared, which is just x squared. I'll write one more. P times p minus 1 times p minus 2 over 3 factorial times x minus 0 cubed, which is just x cubed. Don't forget your plus dot dot dots. This goes on forever unless p happens to be a positive integer like 1 or 2 or 3 or 4 or 5, etc. If p is a positive integer, then at some point these numerators become zeros. You know, for example, if p is 2, this becomes a 0 right there. And after that point, there still are all zeros, and it becomes a finite polynomial, really, instead of an infinite series. So it's more interesting when p is not a positive integer. If we apply this when p equals -1, so we're doing 1 plus x to the -1, plug in p equals -1. And we're going to ultimately confirm the same answer that we got before. One minus x, 2 negatives make a positive. 2 divided by 2 factorial is 1. Next term, 3 negatives being multiplied makes a negative. -3 factorial over 3 factorial becomes -1. So negative x cubed is what I get, etc. Confirming what we already knew from last time, what I just said a few minutes ago, the geometric series expansion here. For what values of x does this work? This is for, well, okay, I should say equals over here. Equals f of x for the absolute value of x still less than 1. X between -1 and 1 in general. If p is a positive integer, it actually works for all x because, again, the series truncates. After a certain point, all the terms are 0. It's really a polynomial instead of a series if p is a positive integer. But otherwise, p is a fraction, p is negative. P is even an irrational number like pi. This still works, but only over this interval. It seems like this is always the interval, but that's not true. We are going to see examples today where the interval is not this. Right? In fact, maybe, well, okay, very shortly we'll do an example like that. What about square root of 1 plus x? 1 plus x to the 1/2 power. Use the same formula with p equal to 1/2. 1 plus 1/2 x. I'm looking up here. That p gets replaced by 1/2. Next term, p gets replaced by 1/2. Still 1/2 times -1/2. Right? 1/2 minus 1 is -1/2. Divided by 2 factorial. X squared. Next term, I got a p 1/2 times p minus 1, -1/2 times p minus 2 is going to be -3/2. Careful doing fraction calculations in your head. Divided by 3 factorial, x cubed, etc. We should make a habit of simplifying. This becomes 1 plus 1/2 x minus 1/8 x squared, right? 1/2 times -1/2 is -1/4, divided by another 2, you get -1/8. The next one's going to be a plus because 2 minus signs being multiplied gives you a positive. The 3 there can cancel with a 3 there. I'll still be left with a 2 factorial or 2 here when I do that cancellation. Ultimately, I've got 4 factors of 2. 1/16 x cubed. So if you were asked on a test for the first 4 non-zero terms of the Taylor series for square root of 1 plus x centered at x equals 0, this would be the answer. And to say it equals the function, you should say plus dot dot dots. By the way, where this series converges is a different question, a different issue from where it equals the function. The convergence of this series can be completely determined typically by the ratio test for most of the interval convergence. And if you had to think about the endpoints, you probably typically want to think about knowledge you already have, for example, the alternating series test sometimes. Equaling the function is a different question, a harder question, actually. We aren't going to address that until after the exam next week. Is this right? Did I get the right answer? Use Mathematica. Mathematica. What is the series for square root of 1 plus x? X is centered at 0, the a is 0, and I want to see through at least the cubic term with a comma 3. Looks like I got the right answer. But it is an infinite series, and you can have Mathematica compute out to the, for example, 10th degree term by putting a 10 there. And the last thing that you see is a big O of the next higher power of x. Mathematica shorthand for plus dot dot dots. There are higher powers of x that are missing, that are not being shown. Okay. You might wonder, before we can do the next example, what is this good for? Quick answer is lots of things. That may not satisfy you. I will show you a quick example of something it's good for, though it may feel a little phony. Like, what if you wanted to integrate the function square root of 1 plus x from 0 to 1? Actually, that's very doable by hand. Not hard to do by hand. Do a substitution. W is 1 plus x. You'd be integrating w to the 1/2. It'd be definitely doable by hand. It's approximately 1.21895. If for some reason you forgot how to do that integral, technically speaking, you could approximate the integral by integrating a part of its Taylor series. I'll copy and paste this part of it here. Oh, I don't want the big O though. There we go. So if you, for some reason, forgot how to do this integral, you could do this instead. Now, that would be definitely harder to do in this example, but it is giving you a pretty good approximation. Maybe not as good as I was hoping for, but still pretty good. It would be probably better and simpler to use Simpson's rule, to tell you the truth. Though not too bad to do it quickly in Mathematica. I mean, Mathematica, technically the best way to do it is integrate if you forgot how to do it by hand. X goes from 0 to 1. The correct answer to 5 places after the decimal is the 1.21895. Okay, as an indication of one application. Okay, maybe not the best indication, but you could still call it an application. All right, now our examples are going to get a bit trickier. You could say, because of that, you need even more practice. Let's consider the cube root of not 1 plus x, but say 8 plus x. In other words, 8 plus x to the 1/3 power. Doesn't quite look like this up here. Well, okay, doesn't quite look like that. Why? Because I got an 8 instead of a 1. So to use this fact, I need to do a little bit of algebraic trickery. I don't like that being an 8, so factor out the 8. But don't make a mistake. If you factor out that 8, you get x over 8 right there. That's all to the 1/3 power, which is the same as 8 to the 1/3 times 1 plus x over 8 to the 1/3. which in simplest form is 2 times 1 plus x over 8 to the 1/3. I claim this is helpful. Why? Because now I have a 1 there instead of an 8 is the main reason. But you might say, well, I have an x over 8 there instead of an x. How do I deal with the over 8 there? X really is, an arbitrary symbol representing an arbitrary number. And I'm saying this 1 plus x to the p power does equal this when x is between -1 and 1. I could use a different letter if I wanted to. I could call it r, for example. X over 8 represents an arbitrary number. Maybe that's the r, if you wanted to use a different letter. What I'm trying to say is I can use this series here, replacing all the x's with x over 8. X over 8 is playing the role of x, with a 2 out front and with p equal to 1/3. So that's going to give me 2 times, in parentheses, look right here, 1 plus p is 1/3. Replace the x with x over 8, not x. Plus, these fractions are going to get a little crazy here. 1/3 times p minus 1 is going to be -2/3 divided by 2 factorial. Replace this x with x over 8. Get x over 8 quantity squared. Plus, go to the next one. 1/3 is p. P minus 1 is -2/3. P minus 2 is -5/3. All over 3 factorial. Replace this x with x over 8. That's got to get cubed. Plus ... Now simplify. Fun. Do I have to simplify? If I ask you to, then yes, you do. Distribute the 2 through. 2 times 1 is 2. That's nice. Okay, 2 times 1/24. Right? That's 1/12. 1/12 times x. Now it starts to get more complicated. 2 there cancels with the 2 factorial because 2 factorial is 2. But I still have a 1/3 times -2/3 is -2/9 times really 1/64, right? 8 squared 64. -2/9 times 8/64. The 2 would cancel with the 64 to leave a 32. What's 9 times 32? 288 minus 1 over 288 x squared. That one was bad. Imagine doing this one. Okay, let's do it. Multiply by 2. Maybe we should just be really careful here. There will be a plus sign because of 2 negatives making a plus. 2 times 5 is 10 times 2 is 20. 3 times 3 times 3 is 27. 3 factorial is 6. 8 cubed also is down there. And let's now just simplify this fraction by itself. That's 20 over what? Some huge number. 20 over 27 times 6 times 8 to the 3rd power is 82,944, which is divisible by 2. So that fraction can be reduced, it looks like, to 10 over 41,472. Did I make a mistake, or is that right? I did up at the top, yeah. Divide by 2 again. Did I forget to do that? Through 2 times That is the 23. Divide by 2 again. Okay, yeah. It's divide by 2 again. 5 over 20,736. Okay, that looks better from what I remember from the last class. Let's see if it's right. So series cube root of 8 plus x. 8 plus x to the 1/3 power. Look at through that term. Yes, that looks good. Okay. But Mathematica can do more. Okay, I could put really high powers there too. Interval of convergence is different this time. Why? Because in using this right here, I replaced all those x's with x over 8s. This one converged when x was between -1 and 1. So this new one's going to converge when x over 8 is between -1 and 1. X itself is between -8 and 8. So this is true for the absolute value of x over 8 being less than 1, which means x itself has an absolute value of less than 8. So x itself is between -8 and 8. That's the interval of convergence. And the radius of convergence is 8. This interval is centered on 0. The distance between the center and either endpoint is 8. By the way, it seems like all these examples have been centered on 0 and the radius was equal to the right endpoint, but that's not always the case. If your interval is centered on, say, 7 and has a radius of convergence of 4, then the interval of convergence goes from 3 to 11. Possibly including the endpoints, possibly not.